Hello everyone, and welcome back to Relax with EEG Facts video number 2. Tonight, we're continuing our journey through Willie's treatment of epilepsy 7th edition. We've arrived at Chapter 7, Localization and Field Determination in EEG. This chapter is about one of the most fascinating and practical aspects of EEG, figuring out where in the brain activity is coming from and how the electrical fields spread across the scalp. It's a detective work of EEG. Every sharp wave, every spike, every rhythm has a story to tell about its origin. Now don't worry, this isn't a technical lecture. Think of it as a slow walk through a very detailed map. I'll guide you through the landmarks, and all you have to do is listen. We'll cover how localization works, why field determination matters, and what it all means for epilepsy diagnosis. So settle in, maybe dim the lights, take a breath, and let's gently explore what I learned about the world of localization and field determination in EEG. Let's begin. Section 1, Localization and Mapping. The word electroencephalogram, or EEG, comes from the Greek roots for electrical picture of the brain. That's a fitting name because when an electroencephalographer sits down to read a tracing, they're really holding a moving portrait of the brain's activity. One of their constant tasks is to imagine this activity in 3 dimensions, building a mental map of where signals are coming from, how strong they are, and how they spread across the scalp. The challenge is that, in theory, there could be countless possible sources inside the brain that create the same pattern on the surface. Despite that, skilled readers are trained to narrow it down to make the most likely, best guess about where an abnormality begins. Localization, finding the source, and mapping, tracking the field it creates, are 2 sides of the same coin. Both are essential, especially when evaluating epileptiform discharges. After all, pinpointing where seizures start can make the difference in choosing the right treatment and even whether someone might be a candidate for surgery. Early pioneers in EEG knew this was important. Back in the 1930s, researchers like Adrian, Matthews, and Walter began using something called phase reversal to localize rhythms. Gibbs and Gibbs even made it a centerpiece of their classic EEG atlas in 1941. Today, we know that a phase reversal doesn't always mean something is abnormal. It can happen with normal rhythms too. But when it appears on a sharp epileptiform discharge, it's still a powerful visual clue. Even with decades of study, no single simple manual method has been universally agreed upon for localization. Most textbooks focus on the so-called forward problem, predicting what the scalp pattern would look like if you knew exactly where the source was. With digital EEG, new software can now attempt the reverse, estimating the source directly from the scalp recording. These computer models are fascinating, but they have their limits and they're not yet part of everyday EEG practice. A more practical, step-by-step approach has been developed at centers like the Cleveland Clinic, where careful visual analysis still remains the standard. The key steps are twofold. First, determine the electrical field at the surface by knowing your electrode positions and head shape. That part has only one right answer. Second, attempt source localization. That part can never have a single unique solution. Instead, you combine neurophysiologic principles, assumptions, and experience to make the most plausible interpretation. Clinically, epileptologists rely heavily on localizing interictal spikes, those brief, sharp waves seen between seizures. These spikes help guide surgery planning, though there's ongoing debate about how well the irritated zone overlaps with the true epileptogenic zone. Still, spikes remain one of the most useful tools we have for mapping out seizure networks. So at its heart, localization and mapping is about turning lines on paper or pixels on a screen into a three-dimensional vision of the brain at work. It's detective work with electricity, and every spike is a clue. Section 2. Practical concepts of electrical fields applied to brain generators. Subsection 1. Sources. When we record an EEG, what we're really seeing on the scalp is just a shadow, a two-dimensional projection of the electrical currents happening deep inside the brain. These currents are generated mainly by populations of pyramidal neurons in the cerebral cortex. Their long, vertical dendrites act like tiny electrical antennas, creating what we call current dipoles. Most of the EEG signal, both normal rhythms and epileptic discharges, comes from two simple ingredients: excitatory signals at the surface of those dendrites and inhibitory signals deeper down. When enough neurons fire together in synchrony, their activity adds up. That summation becomes strong enough that we can detect it at the scalp as a wave, a spike, or even a field spreading across several electrodes. Scientists describe this with something called the equivalent current dipole, or EECD. Sometimes it's just one, other times it's a whole sheet of dipoles across a patch of cortex. Either way, what shows up on the EEG is not the full object itself, but its electrical shadow. Now here's where it gets tricky. Figuring out what's happening on the surface if you know the source inside, that's called the forward problem. It can be solved with math and physics using equations that describe how charges move through tissue, but trying to go the other way, looking at the surface pattern and guessing the exact source inside, that's called the inverse problem. And that one has no single answer. Why? Because the same scalp pattern could come from many different brain configurations. A single dipole right under the electrode, a curved sheet of activity, or even a deep generator spreading widely could all look nearly identical on the surface. Add in differences in head shape, tissue properties, and the limited number of electrodes, usually just 20 to 30 in a routine EEG, and the puzzle becomes even more uncertain. So clinicians use some simplifying assumptions. We often assume the source is close to the surface, perpendicular to the cortex, and that our electrodes are placed well enough to pick it up. Under these rules, if we see one clear maximum on the EEG, we assume the generator is somewhere beneath it. But even then, it isn't perfect. For example, signals from deep inside the brain can spread out so widely on the scalp that they're almost indistinguishable from large superficial sources. Researchers like Jayakar and colleagues have shown how orientation, anatomy, and variations in conductivity can all distort the map, making localization even harder. Which means one of the golden rules in EEG is this: the place where you see the biggest spike on the surface doesn't always mark the true center of the activity in the brain. It's a reminder that EEG is both science and art, a mix of physics, physiology, and the experienced eye of the electroencephalographer. Subsection 2. Volume conduction. When electrical currents travel through the brain, they don't stop neatly at one point. Instead, they spread out in all directions through the tissue and fluids of the head. This process is called volume conduction. Think of it like dropping a pebble in water. The ripples move outward instantly, following countless paths. In the brain, the currents generated by neurons spread through the extracellular fluid, traveling passively without being regenerated by other cells. And they move fast, reaching all the recording electrodes at essentially the speed of light. Of course, distance matters. The further you move from the source, the weaker the potential becomes. This follows what's called the inverse square law. For example, if a cortical source produces 100 microvolts just 1 centimeter beneath an electrode, that same signal would shrink to only 4 microvolts at 5 centimeters away, and just 1 microvolt at 10 centimeters away. The deeper the generator, the more gradual the fall off, producing what's known as a far field potential. Look at the image on the screen if you'd like for reference. Notice how the curve flattens out as distance increases. The head isn't a uniform medium though. Currents encounter different layers: cerebrospinal fluid, skull, scalp, and each has different levels of resistance. As the signal passes through, it gets altered. It may stretch out, smear, or lose amplitude. The skull is especially important. It conducts electricity more easily along its surface than straight through, which spreads the signal out like smudging paint on paper. There are also shortcuts in this pathway. Natural openings in the skull, like foramina or defects from trauma or surgery, can act as low resistance tunnels. Currents are drawn toward these openings, which can distort the electrical field in surprising ways. In fact, electrodes near these defects often pick up unusually high signals, even if the true source is several centimeters away. So volume conduction is both a blessing and a complication. It allows us to detect brain activity from the scalp, but it also means what we see is filtered, stretched, and sometimes distorted by the very structure of the head. Subsection 3. Surface electrical manifestations. When we record brain activity at the surface of the scalp, things aren't always as straightforward as they seem. The way a dipole is oriented inside the brain changes how it shows up on the EEG. Most of the time, cortical dipoles are oriented vertically, radially, relative to the scalp. In that case, an electrode usually sees either the positive pole or the negative pole, but not both. But when a dipole lies at an angle, like those buried in the sulci or fissures, the pattern changes. Nearly 70% of the cortex sits within these sulcal depths, so angled dipoles are more the rule than the exception. This leads to some unusual surface patterns. Instead of the familiar bell-shaped distribution, the field can take on an S shape with two maxima of opposite polarity and a strip of zero activity in between. Look at the image on the screen, figure 7.2 if you'd like. It shows how a cortical discharge can produce both positive and negative peaks on the surface, separated by a boundary line of silence. This can sometimes trick us. For instance, two separate temporal spikes that are nearly synchronous but slightly out of phase may look like one huge transverse dipole stretching across the head. In reality, they're often just two independent generators. Using a different reference montage or noting that the spikes don't always line up helps reveal the truth. Depth also plays a role. The deeper the generator, the smaller the recorded potential becomes, and the wider it's spread across the scalp. Deep sources often appear flat, especially in bipolar montages. Referential montages can highlight them better, but sometimes no scalp reference is clean enough, and invasive electrodes are the only way to see clearly. Surface recordings also get complicated when multiple sources overlap. A superficial generator can overshadow a deeper one. Potentials may reinforce each other, or cancel out entirely, and because an electrode picks up signals within a cone-shaped field, its view of the brain includes both nearby and distant activity. It's also important to remember that the concept of a single dipole is an abstraction. Real epileptogenic zones involve patches of cortex, sheets of dipoles covering several square centimeters at different depths and angles. The result is a mixture of reinforcement, cancellation, and broad smearing on the scalp. One way to think about this is with the solid angle rule. The amount of potential seen by an electrode depends on how much of the active cortical patch falls within its three-dimensional cone of view. Sometimes surprisingly, an electrode farther away will pick up a larger signal than one closer in. Look at figure 7.3 on the screen to see this illustrated. Notice how electrode B, though more distant, records a bigger potential than electrode A because of the way the dipole sheet is oriented. In some cases, opposing dipoles even cancel each other completely, creating what's called a closed field. These invisible generators don't show up on the scalp at all and are usually only detectable with invasive recordings. This is especially common in complex, folded areas like the hippocampus and basal temporal lobe. Finally, the head itself complicates matters. Between the brain and the scalp lie concentric layers, CSF, meninges, bone, and skin, each with different conductive properties. These layers spread out and blur the signals, making small focal discharges appear broader on the surface. In theory, advanced math could help recover the true source, but only if the head were a perfect sphere with electrodes placed anywhere. In reality, the head is irregular, with no easy way to place electrodes on the face or neck where some signals might project. All of these factors remind us that scalp EEG is an indirect view. It captures electrical whispers from deep and folded structures reshaped by anatomy and physics before they ever reach the electrode. Subsection 4. Electrode placement as spatial sampling. When we place electrodes on the scalp, we're really sampling space, taking snapshots of how electrical fields spread across the head. The density of this sampling matters. Too few electrodes and we miss important details. Too many, and the information becomes redundant, harder to interpret. One problem that can happen with too few electrodes is aliasing. That's when the field looks deceptively simple because we don't have enough sampling points to capture its true complexity. Imagine trying to trace the curve of a wave with only 2 points. You'd miss the shape entirely. For a discharge inside the brain to be visible at the scalp, a large enough population of neurons has to fire together. Early studies using cadaver models suggested at least 6 square centimeters of cortex needed to be active for a spike to show up. Later studies, including those with simultaneous scalp and intracranial recordings, found that in reality it takes even more, 10 to 20 square centimeters or more of synchronized cortex to be seen at the surface. This is why some regions, especially the mesial temporal lobe, are so challenging to capture on scalp EEG. The inferior parts of the head just aren't well covered by the standard electrode arrays. Some researchers argue you can pick up these deep spikes from the scalp, while others say it's nearly impossible unless nearby cortex is also involved. For example, one study showed that isolated hippocampal spikes alone couldn't be detected on scalp EEG, but when both the hippocampus and basal temporal cortex fired together, the activity appeared. Special electrodes like sphenoidals can give us a better view of these hidden regions. Look at the image on the screen. Figure 7.4, you'll see a spike that's clearly visible in the right sphenoidal electrode, but almost invisible in the standard double banana montage. That's why epilepsy monitoring units often rely on these specialized placements for difficult cases. The most widely used system for electrode placement is the International 10-20 system. It's reliable, reproducible, and practical, but it has limitations for precise localization. To avoid aliasing, electrodes ideally should be spaced no more than 2.5 centimeters apart. In advanced cases, especially when using computerized source localization, dense arrays with 128 electrodes, each about 2 centimeters apart, may be needed to fully capture the contours of the field. So electrode placement is never just routine. It's a balance between practicality and precision, sampling the brain's rhythms in just the right amount of detail to see what's truly there. Subsection 5, boundary problems. Even with the best electrode setup, there are always edges to what we can see. These are called boundary problems. For localization to be accurate, the maximum potential should fall well inside the grid of electrodes, not right at the border. If a sharp wave looks strongest at the very edge of the array, we can't know for sure how far the field extends beyond it. The brain activity could keep spreading into an area we simply didn't record. This is a common issue with discharges from mesial temporal structures. In the standard 10-20 system, those regions often fall just outside the field of coverage. When the strongest activity rides up against the boundary, we may need to remontage, that is, reorganize or expand the setup to include more electrodes. Sometimes that means adding extra sensors and positions that go below the usual scalp borders. Of course, not all areas of the head are easy to reach. Important regions like the basomesial temporal cortex are tucked deep inside. And standard scalp electrodes can only give us an indirect view. In these cases, extra placements are helpful. Systems with denser spacing, like the 10-10 system, or additional electrodes such as sphenoidal leads, can provide a much clearer picture. In fact, using these extra electrodes often reduces the need to move straight into invasive monitoring. Boundary problems are a reminder that EEG is only as good as the window we provide. Expanding that window carefully and thoughtfully can make all the difference in seeing what's really happening. Section 2, EEG instrumentation considerations related to localization. Subsection 1, differential amplifiers. At the heart of every EEG machine is a device called a differential amplifier. Its job is simple but essential. It compares two input signals, subtracts one from the other, and amplifies the difference. This subtraction step is powerful. It cancels out anything the two inputs have in common, what we call common mode signals, like background noise that affects both electrodes equally. That's why differential amplifiers are so effective at pulling out the true brain signals we care about. Traditionally, the inputs were labeled G1 and G2, dating back to the days of vacuum tube amplifiers. Today, with modern integrated circuits, we usually just call them input 1 and input 2. One thing to remember is that the amplifier itself has no idea what positive or negative means. It doesn't think in terms of polarity, it just does the math. It multiplies the difference by the gain and sends that to the output. This can be a little counterintuitive. Beginners sometimes assume that an upward deflection means positive and a downward one means negative. But in EEG, those are just directions on the page. The true meaning of polarity only comes when you interpret the waveform in the context of the underlying brain generators. To illustrate this, look at figure 7.5 on the screen if you'd like. It shows 4 different input conditions, all producing the exact same output. Whether input 1 is more negative than input 2, or input 2 is more positive than input 1, the differential amplifier processes them the same way. In every case, the spike looks identical at the output, even though the inputs and polarities differ. The key point is this: EEG amplifiers don't show us polarity directly. They show us differences. It's up to the electroencephalographer to interpret those differences and connect them back to the physiology of the brain. Subsection 2, Polarity Conventions. In EEG, when we talk about deflections, we're really just describing the direction the pin or digital trace moves on the screen. An upward deflection means one thing, a downward deflection means another. But it's important to remember these movements are conventions of the instrumentation, not absolute truths about the brain's polarity. By EEG convention, an upward deflection happens when input 1 is more negative than input 2. A downward deflection happens when input 1 is more positive than input 2. That's it. It's simply the difference between the two inputs, not their actual underlying polarity. When we write the name of the electrode connected to input 1 above the trace and the name of input 2 below, the deflection always points toward the electrode with the relative negativity. Look at figure 7.6 on the screen if you'd like. It shows how the differential amplifier processes these differences and how the naming convention makes it clear which electrode is more negative. If the two inputs are equal, if they're on the same isopotential line, then there will be no deflection at all, even if both electrodes are sitting right on top of a strong field. The amplifier only cares about the difference between them. Some amplifiers in research and clinical evoked potential studies flip this convention, showing positive input 1 as an upward deflection, but in clinical EEG, the standard is universal. Input 1 more negative than input 2 equals an upward trace. So when we read EEG, every peak and valley we see is relative. It's not just about the wave going up or down, it's about which electrode is carrying more negativity at that moment in time. Section 3, Electrical Field Determination on the scalp. Subsection 1, Identification of peaks, measurement of the amplitude. When we look for interictal epileptiform discharges, two things guide us: their morphology, that striking sense of standing out from the background, and their field distribution across the electrodes. Both matter because true epileptiform activity must form a realistic pattern that makes sense topographically. When choosing a discharge to localize, it's important to pick a spike that represents the patient's overall population and one that is as free from artifact as possible. In theory, every activity begins at a 0 point, then rises to a maximum. Amplitude is measured from that baseline to the peak, but in practice, finding the true baseline is often difficult. Background rhythms, noise, and overlapping activity can obscure it. Filtering sometimes helps, especially when sharp epileptic activity can be distinguished from slower background waves. Amplitude may be measured as peak to peak or baseline to peak. This becomes trickier with polyphasic discharges where multiple phases occur quickly and don't line up neatly. In those cases, it's essential to identify the maximum amplitude across all channels at the same time point. Montage choice also influences how we see peaks. Different montages can make the same activity look very different, sometimes even suggesting false phase reversals. Look at figure 7.7 on the screen if you like. On the left, the tracing looks confusing with multiple phase reversals, but when the timescale is doubled on the right, it becomes clear the discharge actually has 3 distinct phases, each reaching its peak at slightly different times. What first appeared to be a phase reversal was simply a timing issue. Errors in choosing the right peak or the right time point can lead to major mistakes in localization. This is true even in computerized methods, where a misplaced time marker can displace the apparent source by extraordinary amounts. Clinically, the peak of a sharp wave, usually the negative deflection, tends to have the highest amplitude at the electrode nearest the cortical source. Sometimes a small opposite deflection comes just before the main spike. These early components are usually more focal and more synchronous than the later slow wave that often follows. For that reason, the initial sharp deflection usually contains the most reliable localizing information, so when analyzing peaks, the lesson is clear. Timing matters, montage matters, and early components often tell the truest story about where the activity begins. Subsection 2. Mapping the electrical field. Mapping is the process of turning scalp recordings into a picture of how electrical fields spread across the head. Think of it like drawing contour lines on a topographic map. Except instead of mountains and valleys, we're tracing regions of equal electrical potential called isopotential lines. The process begins by identifying the electrode where activity is strongest. From there, regions further away will show lower amplitudes. By connecting these values, we can create contour lines that illustrate the electrical field. Importantly, EEG potentials are always measured relative to a reference. The absolute values may change depending on the reference you choose, but the shape of the contours remains the same. Look at figure 7.8 on the screen if you'd like. See how the overall field pattern doesn't change no matter what reference electrode is used. Mapping can be done manually without fancy equipment, simply by comparing amplitude relationships between electrodes. First, you trace a chain of electrodes, longitudinally or transversely, to see the one-dimensional pattern. Then you connect chains through common electrodes, building a two-dimensional map. Figure 7.9 illustrates this. On the top, you'll see a bipolar montage, and on the bottom, a referential montage. Both give slightly different details, but the overall maximum field ends up in the same location. To make this quantitative, we usually assign the maximum a value of 100% and the minimum a value of 0%. But there's a subtlety here. Whether that maximum is defined as the strongest negative or the strongest positive depends on assumptions about the generator. As shown in figure 7.10, if you assume the wrong polarity, the map can look very unphysiologic. Choosing the correct polarity helps confirm that the discharge has a realistic distribution, in this example, a maximum negativity in the left temporal region. The best mapping occurs when the reference electrode is truly uninvolved, when it records no activity. In this case, all active channels deflect in the same direction, and the electrode closest to the generator shows the largest deflection. This makes it easy to spot the maximum and gauge the extent of the field. Figure 7.11 demonstrates this beautifully. On the left, a bipolar montage shows no phase reversal, making localization difficult. But on the right, when a contralateral, uninvolved electrode is used as the reference, the left posterior maximum of the discharge becomes obvious. The actual steps for mapping can be summarized simply. 1. Measure the amplitude at each channel. 2. Pick an electrode that looks uninvolved and assign it a value of 0. 3. Calculate all other amplitudes relative to that electrode. 4. Connect chains through common electrodes. 5. If necessary, choose a second 0 electrode for chains without overlap. 6. If the map looks unphysiologic, flip the polarity assumption. 7. Draw the isopotential contours around the field. Recording with multiple montages, especially crisscrossing ones, makes this process more reliable, since you can cross-check the field from different perspectives. In the end, mapping is about translating numbers and waveforms into a spatial picture, giving us a clearer window into where the activity begins and how it spreads. Subsection 3. The bipolar montage. In EEG, a bipolar montage links electrodes together in chains. The output of one electrode pair flows directly into the input of the next, creating a sequence along transverse or sagittal lines. No single electrode is shared by every channel. Instead, each is connected in a chain-like pattern. One of the most important clues in a bipolar montage is the phase reversal. This happens when two adjacent channels deflect in opposite directions at the same time. Phase reversals can be negative when the deflections point toward each other, or positive when they point away. In either case, the reversal marks a critical spot, the location of a maximum or a minimum in the electrical field. Whether that spot is interpreted as the maximum or the minimum depends on the assumed polarity of the generator. For example, surface negative activity produces a negative phase reversal with deflections pointing toward each other. But the same picture could also represent a positive minimum if that's the way the field is oriented. If there is no phase reversal, then the maximum must lie beneath either the first or last electrode in the chain. Figure 7.12 on the screen illustrates this. You'll see how, if the discharge is assumed negative, the activity localizes neatly at the beginning of the chain with a realistic fall-off. But if you assume it's positive, the activity shifts to the end of the chain, producing an odd and unphysiologic distribution. Another subtlety in bipolar montages is amplitude. It can be misleading. Remember, bipolar derivations don't measure absolute voltage at an electrode. They measure the difference between two electrodes. That means the steepest gradients will appear as the largest amplitudes, even if the true maximum lies elsewhere. Look at figure 7.13 on the screen. At first glance, you might think the largest deflection marks the maximum, but in reality, the discharge is shared equally between two adjacent electrodes, F7 and T7. The phase reversal confirms that both are involved. So in bipolar montages, it's not about chasing the tallest spike, it's about watching carefully for phase reversals, understanding gradients, and remembering that what you see is the difference between electrodes, not the absolute maximum itself. Subsection 4. The referential montage. In a referential montage, every channel is connected to the same reference electrode. That reference might be the ear, the mastoid, or a combination of electrodes, but the key is that input 2 is the same across the entire montage. Because of this, only channels sharing the same reference should be analyzed together. When there's no phase reversal, the reference electrode itself must be either the minimum or the maximum of the electrical field. If the reference is the minimum, the largest deflection will occur at the electrode sitting closest to the maximum. This is the easiest situation to interpret because the amplitude of each channel directly reflects how active input 1 is. Look at figure 7.14 on the screen. You'll see how a contralateral, uninvolved reference makes it simple to localize a spike spread across the left temporal region. If, instead, the reference is the maximum, then the channel with the largest deflection points us to the minimum of the field. In this case, electrodes showing no deflection at all must also be sitting at the maximum since they're at the same potential as the reference. But when there is a phase reversal in a referential montage, the story changes. It means the reference isn't clean, it's involved. In other words, it's sitting at some intermediate potential. Some electrodes are more negative than the reference, some less negative, and those equal to the reference show no deflection at all. This can make localization tricky. Look at figure 7.15 on the screen. Here, the same discharge shown earlier in figure 7.14 now looks very different. Because the chosen reference was involved, a phase reversal appears that complicates interpretation. The spike is still the same, but the picture looks confusing, all because of the reference electrode. This is why choosing the right reference matters so much. An uninvolved, quiet reference provides a clear picture. An involved one can create phase reversals that aren't truly there, leading to errors in localization. Subsection 5, Choice of a Reference. In a referential montage, any electrode can serve as the reference. But for localization, the best choice is one that's completely uninvolved, a quiet electrode outside the field of interest. It's important to remember that the voltage difference between any two electrodes is independent of the reference. Subtracting electrode B from electrode A will give the same result as recording the bipolar derivation A-B, no matter which reference is used. This principle makes it possible to reformat montages on modern digital EEG systems with just a click. Still, the reference we choose shapes how the activity looks on the screen. If the reference is uninvolved, say far from the spike, then all the active channels will deflect in the same direction. This makes it much easier to see the field maximum. But if the reference is involved, sitting at some intermediate potential, the tracing becomes confusing. Some channels point up, some down, and localization becomes harder. That's why electroencephalographers usually pick the electrode farthest from the activity as the reference. CZ at the vertex is often a good choice for temporal spikes, but during sleep it can be too active to serve reliably. The linked ears reference connecting A1 to A2 is another common setup, especially for reducing ECG artifact. But it has a hidden drawback. It shunts activity between the two hemispheres. If temporal spikes spread to the ipsilateral ear, they can appear on both sides, creating a false impression of symmetry. Digital systems also offer calculated references. The most common is the common average reference, which combines all electrodes mathematically. It's convenient and widely used, but it has three weaknesses. First, the abnormal activity contaminates the average itself. Second, the signal of interest gets slightly reduced. And third, strong focal discharges show up across all channels with apparent opposite polarity. Another option is the surface Laplacian, also called the source derivation. This method emphasizes local activity and reduces the blur of widespread fields. Some have called it the best reference, but it can mislead if distant electrodes are active. Their influence is weighted more heavily. Other techniques, linearly weighted averages, infinity references, and standardization methods have all been developed, but each comes with trade-offs. The lesson is simple. There is no perfect reference for all cases. Whenever possible, the safest approach is still the most practical one, manually selecting a quiet, uninvolved electrode as a reference. And that's it for Chapter 7 of the Willie's Treatment of Epilepsy textbook. I hope you join me for the next video where we'll be going over Chapter 8. Thanks for watching, and I'll see you in the next video.